Nearly 1 billion miles from where you sit, a planet spins so fast its day lasts only 10 hours, surrounded by rings wider than 30 Earths laid side by side. If you stepped onto its first explorer ship today, you would watch your home planet shrink to a single blue dot, then vanish. You would face diamond rain, winds faster than a bullet, and a moon with seas of liquid gas. If you're enjoying mind-bending space stories, hit that like button and subscribe so you never miss one. By the end of this, you'll understand why the first human to reach Saturn would never come back. Prepare yourselves. We begin. Picture this. You're standing on your front porch looking up at a small yellow dot in the night sky. That dot is Saturn, and between you and that dot stretches a gap so massive, so absurdly vast, that your brain refuses to truly understand it. Saturn sits nearly 1 billion miles from Earth on its closest approach. When it swings farther away, that number balloons past 1 billion miles. To put that in something you can actually feel, imagine driving a car at highway speed, without ever stopping. No bathroom breaks, no sleep, no traffic. Just 60 miles per hour, forever. You would reach Saturn in roughly 1,900 years. Generations of your family would live and die before the car arrived. Light itself, the fastest thing in the universe, takes about 80 minutes to cross that gap. When you wave at a friend across the room, light bounces off your hand and into their eyes almost instantly. But a wave sent from Saturn would take longer than most movies to reach Earth. By the time anyone saw you waving, you would have already moved on to something else entirely. Now here's the part that messes with your head. The fastest spacecraft humans have ever built, the Parker Solar Probe, screams through space at roughly 430,000 miles per hour. Even that machine, designed to outrun stars, would still need years to reach Saturn from Earth. And no crewed vehicle comes close to those speeds. The fastest ship ever to carry humans was Apollo 10, and it topped out at around 24,000 miles per hour. At that pace, a human crew would need about 4 years just to arrive at Saturn's neighborhood. 4 years of canned food. 4 years of staring at the same walls. 4 years before anyone could even start the dangerous work of slowing down. And slowing down is the next problem. You can't just hit a brake pedal in space. To enter orbit around Saturn, your ship would need to burn fuel for hours, possibly days, to shed enough speed. Miss that window, and you fly past Saturn forever, drifting into the empty dark between stars. There's no Coast Guard, no rescue mission, no second attempt. Now consider what you'd be leaving behind. Earth occupies a sweet spot in the solar system. Warm temperatures, breathable air, liquid water, a magnetic field that shields you from cosmic radiation. The instant you leave low Earth orbit, every single one of those protections vanishes. And by the time you reach Saturn, your home planet wouldn't even look like a planet anymore. From Saturn's distance, Earth shrinks to a pale blue dot, dimmer than most background stars. You could cover it completely with your thumbnail held at arm's length. That single image, more than any technical hurdle, breaks the people who train for these missions in simulation. Looking back and seeing your entire world reduced to a flicker, indistinguishable from the millions of other flickers scattered across the dark, realizing that everyone you've ever loved fits behind your thumbnail. But the distance is just the first wall standing between you and Saturn. The real horror begins when you understand what that journey does to your body and mind along the way. Because something about deep space changes humans in ways nobody fully anticipated. 4 years, that's the baseline. 4 years just to fly from Earth to Saturn using the fastest crewed propulsion humanity has ever managed. And that number assumes everything goes perfectly. Every system holds, every calculation lands within tolerance. No micrometeoroid punctures your hull. No solar flare fries your electronics. No human on board suffers a medical emergency that current medicine can't handle in zero gravity. In reality, mission planners build in extra time. They account for orbital alignment, fuel limits, and the brutal math of celestial mechanics. The Cassini spacecraft, an uncrewed probe sent to study Saturn, took almost 7 years to arrive, and Cassini didn't carry the weight of humans, food, water, oxygen radiation shielding, or a return vehicle. A crewed mission would be heavier, slower, and far more complicated. Now picture 7 years of your life inside a metal tube smaller than a school bus. You wake up, you eat the same recycled food, you exercise for 2 hours to stop your muscles from withering. You stare at the same crewmates. You sleep strapped to a wall so you don't drift into a fan. Then you do it again and again, for longer than a child takes to grow from kindergarten through middle school. Here's a strange detail that nobody talks about. Time itself starts to feel different out there. Astronauts on the International Space Station, who only float 250 miles above Earth, report that days blur together within weeks. They lose track of which meal they just ate. They forget what day of the week it is. Now imagine that same disorientation, but stretched across half a decade, with Earth nothing more than a memory. The math gets worse when you consider fuel. Every pound of cargo you bring requires fuel to push it. That fuel itself has weight, which requires more fuel to push, which adds more weight, which requires more fuel. Engineers call this the tyranny of the rocket equation. To send humans to Saturn and bring them home, you'd need a ship hundreds of times larger than anything ever launched. Some estimates suggest the launch mass would exceed every rocket ever built combined. A few proposed solutions exist on paper. Nuclear thermal propulsion could cut the trip down to maybe 3 years. Ion drives, which use electrically charged particles, could in theory push a ship continuously for years, building up speed slowly. There are even theoretical designs for fusion engines that might reach Saturn in under 2 years. None of these technologies exist in working, human-rated form yet. They live in research papers and laboratory tests, decades away from actually carrying a crew. So for now, any real Saturn mission means committing to a journey longer than most marriages last. You'd leave Earth as one person and arrive as someone different. Your skin would thin. Your eyesight would change. Your bones would soften in ways that make returning to gravity painful, possibly crippling. And here's the cliffhanger that haunts mission designers. Even if you survive the trip out, even if your ship arrives intact, even if you successfully enter Saturn's orbit, the math for coming home is somehow worse. Because Saturn doesn't sit still and wait for you. The planet keeps moving, Earth keeps moving, and what looked possible on departure might be impossible by the time you're ready to leave. Which raises the question that nobody likes to answer out loud. Somewhere between Mars and Jupiter, your ship would cross an invisible line. Mission controllers have a quiet name for it: the threshold, the boundary beyond which Earth stops being a destination and becomes a memory. Up to a certain distance, an emergency return is technically possible. Apollo 13 proved this when an explosion crippled their ship halfway to the moon. The crew swung around the lunar surface and used gravity to slingshot home. Mission Control had options, backup plans, tools to improvise. The whole drama played out over 6 tense days. Now stretch that scenario across years and hundreds of millions of miles. Beyond a certain point, there is no slingshot, no return trajectory, no way to point the ship back toward Earth and arrive while the crew is still alive. The fuel won't allow it, the food won't allow it, the orbital geometry won't allow it. Once you pass that threshold, you are going to Saturn whether you want to or not. Astronauts who train for long missions describe the psychological weight of this moment. It isn't a physical line you can see. There's no marker, no buoy, no flashing light. But the crew always knows. They feel it. Some report a sudden quiet that settles over the ship. Others say they look out the window one last time and try to memorize Earth's color, knowing it might be the last time their eyes register that exact shade of blue. Here's something stranger. From far enough out, Earth doesn't look like a planet at all. It becomes a pinprick, a speck, Astronomers call it the pale blue dot, after a famous photograph taken by the Voyager spacecraft from about 4 billion miles away. In that image, Earth occupies less than a single pixel. You could miss it entirely if you didn't know where to look. Every war ever fought, every love story ever told, every human who has ever lived, all crammed into one tiny dot of light. For a Saturn-bound crew, that view arrives surprisingly fast. Within a few months of launch, Earth begins to lose its planetary appearance. By the time you reach the asteroid belt, your home looks like just another star in the background. You can no longer see continents, you can no longer see oceans, you can no longer see the place you grew up. You see a faint dot, and you have to trust that everything you love is still inside it. This is the part that breaks people in simulations. Engineers can train you for emergencies. Doctors can prepare your body for low gravity. Psychologists can drill you on conflict resolution with your crewmates. Nobody can fully prepare you for the moment Earth becomes optional. The moment you realize that if your ship fails out here, no one is coming. The moment you grasp that even if everything goes right, the next time you breathe air that hasn't been recycled 1,000 times will be when you step out onto a moon orbiting a planet that wants you dead. And the thing is, your crewmates feel it too. All of you together in that metal tube, crossing the same invisible line. After that crossing, conversations change. Plans change. Even sleep changes, because something else changes too. Something nobody warned you about. Communication with home starts to lag in ways that fracture your sense of time itself. Send a text message to a friend. Watch how fast it arrives. Almost instantly, right? Now imagine sending that same message and waiting 80 minutes for it to land. Then, waiting another 80 minutes for the reply. A simple back and forth conversation, the kind you'd finish over coffee in 5 minutes, would now take most of your day. That's life at Saturn. Radio signals travel at the speed of light. Nothing in the known universe moves faster. But even light, the fastest thing in existence, needs more than an hour to cross the gap between Saturn and Earth. On the planet's far side from Earth, that delay stretches even longer. Real-time conversation becomes impossible. Not difficult, not awkward. Impossible. Physics simply won't allow it. This breaks something fundamental about being human. We evolved to talk, to respond, to read each other's faces and tones in the same heartbeat. Take that away, and something in our brain starts to misfire. Astronauts on the International Space Station, who can speak with family in near real time, still report intense loneliness after months in orbit. Now imagine that conversation always coming back wrong, out of order, delayed past meaning. You ask a question about your daughter's birthday party. By the time the answer arrives, the party is over, and your daughter is asleep. Your message about a problem on the ship arrives at mission control after the problem has already killed you or solved itself. Here's the weirder part. The delay isn't constant. As Earth and Saturn orbit at different speeds around our nearest star, the gap between them stretches and shrinks. Some weeks the message lag is 68 minutes, other weeks it's 90. Crews would have to plan their communication windows like ancient sailors planning by tides. Send the urgent message now, wait for the response window. Hope you remembered everything you needed to say. Worse still, sometimes the signal vanishes entirely. When Saturn passes behind our nearest star from Earth's perspective, an event called solar conjunction, radio waves get scrambled by the star's churning plasma. Communication blackouts can last weeks. During that time, the crew at Saturn would be completely cut off. No news from Earth, no instructions from mission control, no voices from home, just silence, the kind of silence humans have never lived inside before. Crews would learn to send packets of information rather than conversations, recorded video logs, long, careful written messages, stored data dumps. Imagine writing a letter to your spouse, knowing they won't see it for an hour and a half, knowing their reply won't reach you until the day after tomorrow, You stop talking the way you used to talk. You start talking like someone leaving voicemails for the future. Some space psychologists believe this delay alone is enough to break a crew's mental health within the first year. Not the danger, not the isolation in the technical sense, the simple grinding, hour after hour reality that nobody you love can hear you in time. That every message is a time capsule. That you and your family are now living on different clocks, drifting apart in conversation, as surely as your ship drifts away in space. And the silence between transmissions does something strange to your perception. Time bends, days stretch, and then comes the next problem nobody talks about. Your body itself starts to fall apart in ways doctors back on Earth cannot fix. A funny thing happens to human bodies in space. They start to disappear. Not all at once, not dramatically, just slowly, quietly, day by day. Muscles shrink because they no longer fight gravity. Bones lose calcium because they no longer carry weight. Hearts get smaller because pumping blood through a weightless body takes less effort. After 6 months on the International Space Station, astronauts can lose up to 20% of their muscle mass and 1 to 2% of their bone density per month. Now stretch that across a multi-year voyage to Saturn, and the numbers turn nightmarish. By the time the crew arrives at Saturn, several years into their mission, their bodies would barely resemble what they were on launch day. Their hearts would have shrunk. Their spines would have stretched, sometimes by several inches, because the discs between vertebrae expand without gravity pressing them down. Their bones would be thin and brittle, like the bones of someone 3 times their age. A simple fall, the kind a child shrugs off, could shatter a hip. A small bump against a metal panel could fracture a wrist. Then there are the eyes. Doctors call it spaceflight-associated neuroocular syndrome. In zero gravity, fluid shifts toward the head, putting pressure on the back of the eye. The eyeball itself flattens. The optic nerve swells. Astronauts come back from long missions with vision changes that sometimes never fully reverse. Now imagine your pilot, the person flying the ship, slowly going far-sighted year after year. The instruments blur. The stars smear. Critical readings become guesses. Blood does strange things too. In weightlessness, it pools in the upper body. Crews report puffy faces, congested sinuses, and a constant feeling of being upside down. Their cardiovascular systems get lazy. The heart stops working as hard, which sounds restful but turns dangerous. When they eventually face gravity again, even the weak gravity of a Saturn moon, their hearts may struggle to push blood up to their brains. Many faint on first standing, some collapse entirely. The immune system fares no better. Studies show that astronauts' white blood cells become sluggish in space. Dormant viruses that hide harmlessly inside healthy adults, like herpes and chickenpox, can reactivate. Wounds heal slowly. Infections take hold quickly. Out near Saturn, with no resupply, no fresh antibiotics, no specialist surgeons, a minor cut could turn into a life-threatening crisis. Even sleep falls apart. Without a real day-night cycle, without the gravity that helps your inner ear orient your body, astronauts often sleep poorly for weeks. They drift between exhaustion and insomnia. Their hormones get confused. Some develop a constant low-grade haze of fatigue that never fully lifts. Here's the part that gets engineers arguing. Even if you could solve every other problem of a Saturn mission, you cannot fully solve the body problem. You can exercise, you can take supplements, you can spin parts of the ship to create artificial gravity, but none of that fully replaces what Earth itself provides. Our bodies were built by 1 billion years of evolution on a specific planet with specific conditions. Take a human out of those conditions for long enough, and the human starts to come apart. So the crew arrives at Saturn weaker, thinner, more fragile than they left. And before they can even begin exploring, they have to survive the next horror waiting outside the ship. A storm of invisible particles that can punch holes through their very cells. You can't see them, you can't feel them, you can't shield against them perfectly with any material humans currently know how to manufacture. They scream through space at nearly the speed of light, born in the violent hearts of exploding stars billions of miles away. Cosmic rays. Down on Earth, you're safe from these particles. Our planet's magnetic field deflects most of them. The thick atmosphere absorbs the rest. Together, that double shield blocks the worst of the radiation pouring through the solar system every second. Step outside that protection, and you walk into a hailstorm of high-energy particles, each one capable of slicing through your cells like a microscopic bullet. Astronauts on the International Space Station experience a small amount of this radiation. Even there, just 250 miles up, they absorb roughly 20 times more radiation per day than someone on the ground. NASA limits their cumulative exposure carefully because the risks of cancer, cataracts, and central nervous system damage stack up fast. On a Saturn voyage, the numbers explode. Far from any planetary magnetic field, your ship would receive radiation doses hundreds of times higher than what astronauts get in low Earth orbit. Over the course of a 4-year trip out and a 4-year trip back, the crew would absorb a lifetime's worth of radiation, or more. Studies estimate that without major shielding breakthroughs, every member of a Saturn crew would face a significantly elevated risk of cancer for the rest of their lives, assuming they live long enough for cancer to become a problem. But cancer is the slow killer. The fast killer hides in solar storms. Our nearest star occasionally hurls massive bursts of energetic particles into space. On Earth, these storms produce pretty auroras and the occasional blackout of radio signals. In deep space, with no atmosphere or magnetic shield, a major solar storm could deliver a lethal dose of radiation in hours. The crew would have minutes, maybe an hour, to retreat into a heavily shielded panic room buried inside their ship. Miss the window, and they'd die of acute radiation sickness within days, vomiting, hemorrhaging, watching their immune systems collapse. Designers have tried for decades to solve this. Lead shielding is heavy, which means it requires absurd amounts of fuel to push. Water shielding works but takes up enormous space and resources the crew also needs to drink and breathe. Some engineers have proposed wrapping the ship in a magnetic field generator, an artificial planet's worth of protection bolted to the hull. The technology exists in theory. In practice, no working version has ever flown. The strangest danger comes from the cosmic rays themselves, the highest energy particles. These don't just damage cells, they damage brains. Lab studies on animals exposed to similar radiation show changes in behavior, memory loss, anxiety, and impaired problem solving. The particles smash through neural pathways, leaving tiny tracks of destruction behind. Over a multi-year mission, a crew member could literally watch their cognition slip, forget the procedures they trained for, lose the math they once handled easily, become someone else in the worst possible way. And the radiation is just the universe's first line of defense. Saturn itself has invisible weapons waiting. The planet generates a magnetic field so enormous that it dwarfs the entire planet. Step inside it, and your ship enters an environment that does things to electronics nobody on Earth has ever fully simulated. Saturn doesn't fight visitors with weapons you can see. It fights with invisible fields that stretch farther than the planet itself. Wrap your imagination around this. Saturn's magnetic field extends so far into space that if you could see it with your eyes, it would appear larger than our nearest star in the night sky. The field forms a giant bubble called a magnetosphere, and that bubble dwarfs the planet at its center. Inside this bubble, charged particles get accelerated to vicious speeds, trapped, and slung around the planet in radiation belts that would kill an unprotected human in minutes. Earth has a similar bubble. Ours protects us. Saturn's wants to murder you. The difference comes down to scale and intensity. Saturn's magnetosphere is the second largest in the solar system after Jupiter's. Inside this magnetic prison, Ions and electrons get whipped to such high energies that they hammer everything they touch. Spacecraft passing through these belts have to be specifically hardened with extra shielding around their computers, sensors, and power systems. Even with that armor, electronics can fail, cameras can blind, radios can go silent for hours. For a human crew, the danger gets personal. Time spent inside Saturn's radiation belts is measured not in days, but in minutes before you've absorbed a lethal dose. Mission planners would have to plot trajectories that thread the gaps between the worst belt zones, like sailors picking their way through reefs. One miscalculation, one navigational error, one stuck thruster, and the ship drifts into a region where every second adds to the body count. The field doesn't just trap particles. It creates aurorae at Saturn's poles that put Earth's northern lights to shame. Hubble images show enormous curtains of ultraviolet light dancing across the planet's top and bottom, glowing for thousands of miles. Beautiful from far away, deadly up close. Those aurorae mark the places where the magnetic field funnels lethal particles down into the upper atmosphere. Fly through one, and your ship gets bombarded from all directions at once. Here's something stranger. Saturn's magnetic field has a property that confused scientists for decades. The field appears almost perfectly aligned with the planet's rotation axis. Other planets, including Earth, have tilted magnetic fields. The magnetic North Pole doesn't match the rotational North Pole. On Saturn, they line up almost exactly. Nobody fully understands why. The simplest explanations of how planets generate magnetic fields predict a tilt should exist. Saturn breaks the model. Some scientists theorize that something deep inside the planet, some unusual layer of churning metallic hydrogen, smooths out the field in a way no other world manages. Others think we're simply measuring it wrong. For the crew, the why doesn't matter, the what does. The field acts like a giant generator spinning along with the planet, pumping energy into every charged particle nearby. Inside the magnetosphere, time spent unprotected is time spent dying. Even the ship's metal hull would slowly grow radioactive under prolonged exposure, like a doctor's old X-ray machine left running too long. And the magnetic cage is just the beginning, because once your ship enters Saturn's neighborhood, you discover that the planet has another defense even crueler than radiation. A wall of debris, billions of pieces, some small as sand, some big as houses, all moving fast enough to punch holes through anything humans have ever built. Here's a fact that should worry anyone dreaming of a Saturn voyage. No human being has ever traveled beyond the orbit of the Moon. Not one, not in 50 years of spaceflight. Not in all the missions ever flown. 12 astronauts walked on the lunar surface during the Apollo program. A handful more orbited the Moon without landing. After that, nobody. Every single human in space, since the early 1970s, has stayed within a few hundred miles of Earth's surface, looping endlessly around our home planet, never venturing further. There's a reason for this, and it isn't just money. Beyond the Moon, the universe gets exponentially more dangerous, and our technology stops being good enough to keep crews alive. Going to Mars, the nearest planet humans might realistically visit, is already pushing the boundaries of what current engineering can handle. Going to Saturn is a leap into territory where the rules change entirely. Think about what Mars requires: a 9-month trip in each direction, 18 months on the surface waiting for the next launch window, roughly 3 years total. Multiple international space agencies have been working on this challenge for decades. Nobody has launched a crewed Mars mission yet. The closest attempts remain in simulation, paper studies, and prototype testing. The problems are not impossible, but they are enormous. Saturn multiplies every one of those problems. Take fuel as one example. A Mars round trip needs enough propellant to push humans, supplies, and a return vehicle out and back. Engineers calculate that even with current best technology, the total launch mass approaches the limits of what humanity can lift into orbit. For Saturn, the numbers explode. You'd need to push roughly 6 times the distance, with roughly 4 times the duration. The fuel requirements rise so steeply that some engineers argue chemical rockets simply cannot do it within human lifetimes. You'd need nuclear propulsion, or fusion drives, or something that doesn't exist yet outside laboratory experiments. Take supplies as another example. A Mars crew needs food, water, oxygen, and replacement parts for 3 years. A Saturn crew might need supplies for 8 or 10 years. Every additional pound of cargo means more fuel to push it, which means more weight, which spirals into an engineering nightmare. Even with the most efficient recycling systems ever designed, perfect water recovery, and perfect oxygen regeneration, the crew still needs food. And food doesn't recycle. You can't squeeze a steak out of a recycler, so you carry years and years and years of it, all of it eating into your launch mass, your storage space, your fuel budget. Then there's the human factor. 3 Mars years is hard. 8 to 10 Saturn years approaches the limit of what any species has ever asked its members to endure inside a sealed metal can. Even submarine crews, who hold modern endurance records for confinement, typically rotate out after several months. Stretch that to nearly a decade with no possibility of rescue, and you're testing not just engineering, but the deepest limits of human psychology. So Mars stands as a wall. Until we cross that wall successfully, Saturn remains theoretical, a planet humans dream about but cannot reach. And even if we crack Mars, the technology gap between Mars and Saturn might be wider than the gap between flying and not flying at all. Yet some engineers refuse to give up. They draw rocket designs that exist nowhere except on whiteboards, strange, exotic propulsion systems that promise to change everything. There's just one catch. To send humans to Saturn and back, you would need to break a rule, not a guideline, not a recommendation. A rule of physics written into the fabric of how rockets work. The rule is called the rocket equation, and it's a quietly merciless piece of math. The equation says that for every unit of weight you want to send somewhere, you need a much larger amount of fuel to push it there. And that fuel itself has weight, which means you need even more fuel to push the fuel, which adds more weight, which requires more fuel. The numbers grow exponentially. Quickly, brutally, the equation tells you that beyond a certain distance, no chemical rocket humanity knows how to build can carry humans there and bring them home. Saturn sits past that line. If you wanted to send a crew of 4 to Saturn using only the kind of chemical rockets we currently launch, your ship at takeoff would have to weigh something approaching the mass of a small mountain. The fuel tanks alone would be larger than skyscrapers. The launch facility would need to be unlike anything ever built. And even then, the math barely works. The crew would arrive at Saturn with almost no fuel left for return. They'd be stranded by design, victims of a propulsion technology that hit its ceiling decades ago. So engineers chase alternatives. Some are promising, some are wild. Nuclear thermal propulsion uses a small atomic reactor to heat hydrogen gas, then shoots it out the back of the ship at tremendous speed. The advantage is efficiency. A nuclear thermal rocket can squeeze roughly twice as much push out of every pound of fuel compared to chemical rockets. That doubling matters enormously on a Saturn mission. Trip times drop, fuel needs shrink, survival odds rise. The technology exists in working prototypes from the 1960s, but no nuclear rocket has ever actually flown in space. Political concerns about launching radioactive material kept the engines grounded. Ion engines offer a different path. Instead of burning fuel violently, they accelerate charged particles using electric fields, pushing them out the back at extreme speeds. The thrust is gentle, barely enough to feel, but ion engines can run for years. Slowly, steadily, they build up enormous velocity. Uncrewed probes already use this technology successfully. The challenge is power. To push a human-sized ship to Saturn with ion drives, you'd need massive solar panels, or more realistically, a nuclear reactor to feed the engines. Then come the truly speculative options: fusion drives, antimatter engines, magnetic sail systems that ride the streams of charged particles flowing from our nearest star. Each of these technologies could, in principle, slash Saturn travel times to a year or less. Each of them remains years or decades away from working, human-rated form. And here's the cruel irony. Even if engineers solve the propulsion problem, they still face the rest of the gauntlet: radiation, bone loss, communication delay, food storage, psychological collapse. Solving one piece doesn't solve the others. A faster rocket gets you to Saturn quicker, but it doesn't change what waits when you arrive. And what waits is a world that doesn't behave like anything humans have ever stood on. A planet with no place to land, no surface to walk, nothing solid to step onto at all, just an endless plunge into something that goes on forever. Forget everything you know about planets having surfaces. Forget the idea of landing your ship somewhere safe. Forget the dream of stepping out, planting a flag, and looking around at a strange new landscape. Saturn has no ground. The planet is a gas giant, meaning it's made almost entirely of hydrogen and helium, with a few other gases mixed in. There is no solid crust waiting beneath the clouds, no rock, no ice, no place where you could put your boot down and feel something push back. If you tried to land on Saturn, you wouldn't land, you'd fall, and keep falling, and keep falling, for thousands of miles, through layer after layer of gas, with the temperature and pressure rising until something terrible happened to your ship. Picture it like this. The top of Saturn's atmosphere looks almost peaceful from above. Pale yellow clouds drift in long bands across the planet. The colors come from compounds of ammonia and other chemicals frozen high in the air. If you drop through those clouds, the first few thousand miles would feel like falling through endless layers of fog, each layer thicker and stranger than the last. 100 miles down, the pressure has already climbed to several times what you'd feel at sea level on Earth. A few hundred miles deeper, the pressure crushes your ship as hard as the deepest ocean trenches on Earth. The temperature, which was bitterly cold at the cloud tops, now climbs past the boiling point of water. The hydrogen around you starts behaving in strange ways, transitioning from gas to a thick, soupy liquid. Keep falling, the pressure keeps climbing. Within 1,000 miles or so of where the cloud tops were, the temperature hits thousands of degrees Fahrenheit. The hydrogen has compressed into a substance that doesn't quite behave like a gas or a liquid. Engineers and physicists call it a supercritical fluid, a state of matter that exists almost nowhere on Earth, except in laboratory experiments. Deeper still, things get truly bizarre. Roughly halfway to the planet's center, the pressure is so extreme that hydrogen starts to behave like a metal. Atoms get squeezed so tightly that their electrons can flow freely between them, the defining property of metallic substances. This metallic hydrogen layer, hundreds of times thicker than Earth's entire atmosphere, is where many scientists believe Saturn's enormous magnetic field gets generated. Currents flowing through this electrically conductive ocean of crushed hydrogen create the magnetic cage that surrounds the planet. At the very center, perhaps, sits a solid core, maybe rocky, maybe icy, maybe something stranger. Nobody really knows. The pressures down there exceed anything Earth-based science can fully replicate. The temperatures rival those near the surface of our nearest star. Whatever the core is made of, it sits buried under tens of thousands of miles of crushing material. Untouchable, unreachable, possibly forever unknown. So when astronauts dream of exploring Saturn, they don't dream of walking on it. There's nothing to walk on. The best they can hope for is floating in the upper atmosphere in some kind of armored airship, looking out at the swirling cloud bands, or staying in orbit, or, more realistically, exploring the planet's moons where solid ground actually exists. But before any of that, they'd have to deal with what waits at Saturn's North Pole, something so strange that for years scientists thought their instruments had to be wrong. A perfect six-sided storm bigger than Earth, spinning in a pattern that shouldn't be possible. Around Saturn's north pole, something impossible has been spinning for at least as long as humans have had the instruments to watch it. A storm shaped like a perfect hexagon, 6 clean sides, 6 sharp corners, a geometric pattern bigger than the entire Earth, churning at the top of a gas giant where physics should produce only swirls and curves. Cassini, the spacecraft that orbited Saturn for years, photographed this hexagon over and over. The images are jaw-dropping. A vast geometric shape etched into clouds holding its form year after year while everything around it churns. The hexagon doesn't drift, doesn't reshape, doesn't fade. It just keeps spinning, locked in place, the corners marching around the pole in slow, stately rotation. The hexagon stretches roughly 20,000 miles across. Earth, which measures only about 8,000 miles in diameter, would fit easily inside it with room to spare. The walls of the hexagon plunge tens of miles down into Saturn's atmosphere. Inside those walls, winds scream at hundreds of miles per hour. At the very center, a massive eye rotates, like a hurricane sitting on top of a hurricane sitting on top of a hexagon. Scientists struggled for years to explain how this pattern could exist. Storms on planets don't naturally form into geometric shapes. They make spirals, curls, eddies, random, organic forms. A perfect 6-sided polygon is the kind of thing you'd expect in a snowflake or a beehive, not in a planetary atmosphere where everything is turbulent and chaotic. The current best explanation comes from lab experiments. Researchers built small models of rotating fluids, like spinning tanks of water, with jets injected at the edges. Under certain conditions, when the rotation speed and jet speed combine just right, the fluid forms standing waves that lock into polygonal shapes, triangles, squares, pentagons, hexagons. The math behind it involves something called Rossby waves, large-scale fluid motions that can interlock into stable patterns when conditions align. So Saturn's hexagon might be a giant standing wave, frozen into the upper atmosphere by the precise interplay of wind speeds and rotation rates. That explanation works in theory. In practice, it still feels uncomfortable, because Saturn has been spinning for billions of years. The hexagon presumably has been there for an enormous span of time. How does a pattern that delicate stay perfectly aligned for so long, while the entire rest of the planet's weather chaos rages all around it? For a Saturn-bound crew, the hexagon would be both a destination and a warning. It would be visible from orbit, an enormous geometric mark on the planet that no other world in our solar system displays. Pilots could use it as a navigational landmark, the way ancient sailors used coastlines. But getting close would be suicide. The winds inside the hexagon would shred any ship. The lightning crackling through those clouds carries energy that dwarfs anything ever recorded on Earth. Storms inside the hexagon's walls have been measured discharging bolts of electricity 10,000 times more powerful than the strongest Earth lightning. Yet the hexagon isn't even Saturn's most violent feature. Far from the poles, in the wide bands of the planet's middle, winds blow at speeds that make Earth's most monstrous storms look like a gentle breeze. Speeds so fast that they break the limits of what most weather systems anywhere in the solar system manage to reach. Speeds that would tear a ship apart in seconds. If you could stand inside Saturn's atmosphere for a moment, the wind would not push you. It would erase you. Near the planet's equator, winds rip through the cloud layers at speeds approaching 1,000 miles per hour. Let that number settle. The most powerful tornadoes ever recorded on Earth top out around 300 miles per hour. Hurricane winds peak around 200. A passenger jet cruises at roughly 550 miles per hour. Saturn's equatorial winds blow nearly twice as fast as a commercial airliner flies. Continuously, year after year, forever. These winds don't pause, they don't rest, they don't change direction with the seasons the way Earth's storms do. They are permanent features of the planet, driven by Saturn's fast rotation and the heat rising from deep inside. The wind belts circle the entire planet, stretching tens of thousands of miles wide and tens of miles deep, moving with the kind of monstrous, sustained energy that has no real comparison anywhere in the inner solar system. What would happen if a ship tried to fly through these winds? Pretty much exactly what you'd expect. Metal would shred, plastic would peel, glass would shatter. Even materials specifically engineered to handle high-speed atmospheric entry, the kind of advanced composites that survivor spacecrafts plunge through Earth's atmosphere, would fail in Saturn's equatorial winds. The forces would tear the ship apart before it could descend more than a few miles. Engineers have studied this problem for decades, dreaming of probes that could survive deeper dives into Saturn. The most ambitious designs involve incredibly tough armored shells slowly descending under parachutes, communicating back to orbit until the heat and pressure crush them. Even those probes would only survive for an hour or two before being destroyed. A human mission to dip into Saturn's atmosphere is so dangerous that most engineers consider it scientifically interesting, but practically impossible. Here's a strange detail. The winds change direction depending on depth. At one altitude, they blow east at 1,000 miles per hour. A few hundred miles deeper, they slow and might even reverse. The atmosphere is layered like an onion, with each layer moving at different speeds, sometimes in opposite directions. A ship descending through these layers would get whipped one way, then suddenly the other, with forces that would snap any rigid structure. Lightning bolts thrash through the cloud layers. Cassini's instruments picked up radio bursts from storms on Saturn that were millions of times more energetic than the most intense Earth thunderstorms. Some of the storms were larger than countries. Some lasted for months. One storm system, observed during Cassini's mission, grew so large it eventually wrapped around the entire planet, creating a band of lightning and turbulence stretching from one side to the other. And below the storms, something stranger still drips through the air. Saturn's atmosphere doesn't just contain gas. It contains the ingredients for one of the most surreal forms of weather ever theorized in our solar system. A weather pattern so unusual that for years, scientists weren't sure whether to believe their own models. Diamond rain. The conditions in Saturn's middle atmosphere may be just right to make carbon condense, crystallize, and fall as solid diamonds, some of them tiny, some of them the size of marbles, falling through the gas in slow, glittering showers, deeper and deeper, until the pressure crushes them into something even stranger. The next layer down might be a world humans never expected to find anywhere. Diamonds falling from the sky. It sounds like fantasy, the kind of thing a fairy tale might invent. But on Saturn, the math actually works. Here's how it happens. High up in the planet's atmosphere, lightning storms split methane molecules apart. Methane contains carbon. When the lightning breaks it down, free carbon atoms drift through the air, looking for partners. As they sink deeper into the planet, the pressure starts to climb. The carbon atoms begin to clump together, forming first soot, then graphite, then, deeper still, something extraordinary. Diamond. Pure crystalline carbon, the hardest natural substance known, forms when carbon atoms get squeezed under enormous pressure and heat. The conditions for natural diamond formation on Earth happen deep underground, in mantle layers thousands of miles below the surface. On Saturn, those same conditions appear naturally in the planet's middle atmosphere. The combination of pressure and temperature creates a zone where carbon, after falling for thousands of miles as soot and graphite, finally crystallizes into diamond. So you have, deep inside Saturn, layer after layer of falling diamonds. Some are tiny grain-sized specks. Others might grow much larger, possibly several inches across, depending on how long they've spent falling through the right conditions. Scientists estimate that something like 1,000 tons of diamonds rain through Saturn's atmosphere every year. 1,000 tons, just on Saturn alone. Jupiter, larger and similar in composition, may produce even more. Yet nobody will ever scoop up these diamonds. The depths where they form are completely beyond reach. Even an armored probe couldn't survive the trip down. And the diamonds don't pile up forever. As they sink deeper, the temperature keeps climbing. Eventually, they reach a layer hot enough to melt them. The diamonds dissolve back into a thick, hot ocean of liquid carbon, which then continues falling, possibly merging with the planet's deeper structure. So the cycle goes. Lightning at the top creates carbon. Carbon falls as soot. Soot compresses into graphite. Graphite crystallizes into diamond. Diamond melts into liquid carbon. Liquid carbon vanishes into the depths. All of this happens silently, invisibly, on a scale that humans cannot see and may never directly measure. The strangeness doesn't stop there. Saturn's atmosphere contains other surprises too. Helium, the second most common element in the planet, behaves in odd ways at certain pressure depths. It forms droplets that rain downward, just like the diamonds, sinking through the surrounding hydrogen. This helium rain releases energy as it falls, possibly heating Saturn from within and contributing to the planet's strange property of giving off more energy than it receives from our nearest star. That's right, Saturn produces its own heat. The planet radiates more energy out into space than it absorbs from the star it orbits. The exact source of this internal heat remains debated. The helium rain is one theory. Slow gravitational settling of the planet's contents is another. Whatever the cause, the heat seeps upward through all those crushing layers, driving the storms, fueling the winds, possibly even helping power the magnetic field. For any future Saturn explorers, the diamonds and the helium rain would remain forever out of reach. But there's something else around Saturn, much closer to where a ship might safely orbit, that holds its own dangers. Something so famous, so beautiful, that it shows up in every picture of the planet. The rings. And those rings, gorgeous as they look from a distance, would kill you instantly if you tried to fly through them. Saturn's rings might be the most famous feature in the entire solar system. They show up on schoolroom posters, science fiction book covers, and the imagination of every child who has ever looked up at a star chart. From a distance, they look serene, eternal, almost gentle, like a halo wrapped around the planet. Up close, they would shred your ship into atoms. Here's what people forget about the rings. They aren't solid. They aren't a single sheet of material. They are made of countless billions of individual chunks of ice and rock, ranging in size from grains of sand to boulders the size of houses, to a few pieces nearly the size of small mountains. All of these chunks orbit Saturn at tremendous speeds. The inner rings move faster than the outer rings, the way different lanes of a racetrack move at different rates. Speeds can exceed 40,000 miles per hour. Now imagine flying a ship through that, 40,000 miles per hour, billions of objects, some of them the size of grains, some of them the size of vehicles. Even an impact with a piece of ice the size of your fist would punch through your hull like a cannon shell. The ship would depressurize in seconds. The crew would die before they could even react. Larger impacts would simply destroy the ship outright. A boulder hitting at orbital speeds would release more energy than a small nuclear weapon. There would be no warning. Garin particles are too small for most ship sensors to track individually. By the time you spotted one, it would already have hit you. So how did Cassini, the famous spacecraft that orbited Saturn for over a decade, survive flying near the rings? The answer is careful planning and a lot of luck. Cassini never plunged through the main rings. The mission planners chose orbits that threaded the gaps between rings, the relatively empty zones called divisions. Even then, on the so-called grand finale phase of its mission, Cassini was deliberately sent diving through the narrow gap between the planet's atmosphere and the innermost ring. That gap is one of the cleaner parts of the system, but even there, mission planners worried about dust impacts. The rings themselves are surprisingly thin. They stretch hundreds of thousands of miles wide, but are only a few tens of feet thick in most places. Imagine a flat disk the size of a continent, only 10 or 20 feet thick. The thinness is one reason they look so flat and elegant from far away. Fly above them, and you'd see what looks like a vast glittering plain. Fly through them edge on, and you'd see almost nothing, just a thin streak of light, until your ship hit something. The composition is mostly water ice, pure frozen water reflecting starlight like a mirror. That's why the rings shine so brightly. They are the largest natural mirror in the solar system. Some scientists believe the ice came from a moon that strayed too close to Saturn and got torn apart by the planet's gravity hundreds of millions of years ago. Other moons might have shattered too, contributing their own debris over time. And inside the rings, hidden among the ice and rock, there are objects that don't show up in most pictures. Small mountainous shapes that orbit within the ring material, moving like predators through a sea of prey. Some are easy to miss until they nearly collide with a passing probe. Some carve patterns into the rings themselves, betraying their presence. And one of them in particular behaves in ways that suggest it might not be a simple object at all. Saturn's rings aren't empty between the dust and ice. They have residents. Small worlds, often only a few miles across, that orbit inside the ring material like islands inside a flowing river. Astronomers call them moonlets, and they are among the strangest objects in the entire solar system. Some of them are visible because they sweep clear lanes through the surrounding ice. Pan and Daphnis, two of the better-known examples, orbit inside narrow gaps within the rings. Their gravity pulls nearby ring particles into wavy patterns, leaving wake-like trails behind them. Cassini captured incredible images of these moonlets, showing them as tiny, lumpy objects, looking strangely like flying ravioli or walnuts. Their odd shapes come from ring material that has accreted onto them over time, building up around their equators, like dust collecting on a spinning fan. Other moonlets hide deeper in the ring material, only revealing themselves by the patterns they create. Astronomers sometimes spot propeller-shaped disturbances in the rings, little gaps and ridges that suggest an object roughly the size of a stadium tumbling through, too small to be seen directly but big enough to shape the ice around it. These propellers have been catalogued in the hundreds. There may be many more, hidden in the densest ring sections, where even Cassini's cameras couldn't pick them out. The implication is unsettling. For any ship flying near the rings, the visible obstacles are bad enough. The invisible ones make the danger exponentially worse. A propeller object the size of a building, moving at tens of thousands of miles per hour, would be effectively undetectable until it hit you, or you hit it. Some scientists believe the rings themselves may be made up of countless, slowly aggregating moonlets, with material constantly clumping together, breaking apart, and reforming. The rings might be a kind of low-grade factory, building tiny worlds and tearing them apart again across millions of years. In that view, the moonlets aren't separate from the rings. They are the rings, just at certain stages of their endless cycle. One moonlet has drawn particular attention. Pan, the inner shepherd of a narrow gap in the rings, has such an unusual shape that scientists have debated its origin for years. The moon is shaped like a flying saucer or a walnut, with a strange equatorial ridge that sticks out far beyond what gravity alone would predict. The leading explanation is that ring material slowly accumulated along Pan's equator over time, building up the ridge inch by inch. But the ridge is so pronounced, and the moon so oddly shaped, that some researchers wonder if more is going on. Cassini also discovered that some of the moonlets have very young surfaces, suggesting they may be reshaping or reforming constantly. Material falls onto them, builds up, gets shaken loose by collisions, falls back differently. They are not the ancient fossilized worlds we expect moons to be. They are dynamic, active, changing. For a Saturn-bound crew, the hidden moonlets would be the kind of threat nobody could predict or fully avoid. Every approach to the rings would be a gamble. Every close pass would risk impact with an object the cameras couldn't catch in time. And yet, despite the danger, the moons of Saturn outside the rings hold rewards that no other place in the solar system can match. especially one in particular, a moon with weather, with seasons, with seas, a moon that might be the strangest familiar place humans will ever visit. Beyond Saturn's deadly rings and crushing magnetic field, an entirely different kind of world waits. A moon larger than the planet Mercury, a moon with a thick orange atmosphere, a moon with rivers, lakes and oceans, just not the kind of water humans know. Titan. Titan is the second largest moon in the solar system, after Jupiter's Ganymede. It's bigger than our own moon, bigger than Mercury, big enough that if Titan orbited our nearest star directly instead of orbiting Saturn, scientists would probably call it a planet. The thick atmosphere wrapping around it is so dense that the air pressure at Titan's surface is roughly 50% higher than air pressure on Earth at sea level. You could walk around on Titan in a heavy coat and an oxygen mask. You wouldn't need a full pressure suit. The atmosphere would press against you like deep sea pressure, but not crushingly. The temperature, on the other hand, would freeze you in seconds. Titan's surface sits at roughly minus 290 degrees Fahrenheit, cold enough that water there isn't liquid. It's rock-hard ice, harder than any stone humans build with. The wet stuff on Titan's surface isn't water. It's methane and ethane, same molecules you'd find in natural gas back on Earth, but down here, where Earth is warm, they're gases. On Titan, where the temperature drops far below their freezing points, they become liquids. Titan is the only place in the solar system, other than Earth, where stable liquid pools sit on the surface. Lakes, rivers, even something that could be called rain, when methane clouds drift through the orange sky and let go of their droplets. The Cassini-Huygens mission gave humans the first close look at Titan. The Huygens probe parachuted through Titan's atmosphere in early 2005, sending back images of a landscape with riverbeds, hills, rocks made of water ice, and a wet, slightly slushy surface that looked almost like a beach after the tide had gone out. Then the probe died, frozen and broken, less than 2 hours after landing. 2 hours was enough to change how scientists thought about moons forever. Since then, Cassini has mapped Titan's surface using radar that can see through the thick orange haze. The maps show enormous seas in Titan's northern hemisphere. The biggest, Kraken Mare, would dwarf the largest Great Lakes back on Earth. Methane and ethane sit in those seas, slowly evaporating into clouds, falling back as rain, cutting channels into the ice rock, just like water does on Earth. Titan has a hydrological cycle. The cycle just runs on entirely different chemistry. For future explorers, Titan is one of the few places in the outer solar system where humans could realistically build a base. The atmosphere blocks most cosmic radiation. The pressure is workable. The chemistry is fascinating, with possible complex organic molecules raining down from the upper atmosphere onto the surface in a slow drift. Some scientists even speculate that strange forms of life using liquid methane instead of water might exist in those frozen seas. There's no proof. The chemistry is theoretically possible. The hunt continues. But Titan is just one of Saturn's strange children. Closer to the rings, smaller and brighter, another moon hides a different kind of mystery. A frozen world with cracks in its surface, shooting jets of water vapor and ice high into space. A moon that might be hiding a vast ocean. Enceladus is small, tiny really by moon standards, only about 300 miles across. You could drive across it in a few hours if there were roads and if your car didn't freeze instantly. By size, Enceladus is unremarkable. By what it does, Enceladus may be the most exciting place in the solar system after Earth itself. Cassini discovered something stunning when it flew past Enceladus in 2005. The moon was shooting jets of water vapor and ice particles into space, not from one spot, from an entire region near the South Pole, a place scientists came to call the Tiger Stripes, for the long parallel cracks running across it. Out of those cracks, plumes of icy material burst up hundreds of miles above the surface, some of it falling back, some of it escaping into space. Where was the water coming from? The answer reshaped everything scientists thought about the outer solar system. Enceladus, despite its tiny size and frozen exterior, hides a vast ocean of liquid water beneath its icy crust. A global ocean. Salt water, possibly several miles deep. The ice shell on top might be a few miles thick, but underneath, an entire warm, dark sea sloshes around the moon's rocky core. The heat keeping that ocean liquid comes from tidal forces. As Enceladus orbits Saturn in a slightly elliptical path, the planet's gravity squeezes and relaxes the moon repeatedly. That constant flexing heats the interior the way bending a paperclip back and forth makes it warm. The flexing isn't enough to melt the surface ice, but it's plenty to keep the underground ocean liquid. And where there's liquid water for billions of years, with rock at the bottom and heat keeping it warm, the conditions match many of the prerequisites for life. Cassini's instruments flew through the plumes more than once. They analyzed the spray. The results stunned scientists. The plumes contained salt, suggesting the ocean below interacts with rocky material. They contained organic molecules, the building blocks of biology. They contained molecular hydrogen, which on Earth often hints at hydrothermal vents, the kind of deep-sea features where life first thrived billions of years ago. This doesn't prove life exists on Enceladus. Nothing has been directly observed. The current evidence shows only that the chemistry for life is plausible, but the implications are enormous. If a moon this small, this cold, this far from our nearest star can harbor the right conditions for life, then the universe might be packed with places where life could exist. The galaxy could be teeming with similar ocean moons, quietly, invisibly, hiding under layers of ice. For a Saturn-bound crew, Enceladus would be the highest value target. Land near the tiger stripes. Drill through the ice. Sample the ocean directly. Find out if anything lives down there. Such a mission would arguably be the most important scientific expedition in the history of humanity. Discovering even single-celled life beneath an ice shell on a moon of Saturn would change everything about our place in the universe. But the drilling alone would be a nightmare. The ice shell is miles thick. The temperatures at the surface would freeze your equipment solid. The plumes themselves, beautiful from a distance, would dose anything passing through them with high-speed particles capable of ripping holes in spacecraft. Yet Enceladus, with its hidden sea, is far from the only Saturn moon hiding secrets. There's another one, smaller, stranger, shaped in a way that makes everyone who sees it think the same thing. The first time Cassini sent back clear images of Mimas, the response from the public was instant. People recognized it, not because they had studied space science, not because they knew Saturn's moons by name. They recognized it because it looked exactly like a moon from a famous science fiction movie. A weapon-shaped sphere with a giant round crater on one side, like an enormous eye watching the universe. Mimas is one of Saturn's inner moons, roughly 250 miles across, made mostly of water ice with a small amount of rock. By itself, it would be unremarkable. Small, cold, quiet, except for one feature that dominates everything else about it, Herschel Crater. Named after the astronomer who discovered Mimas in the late 1700s, Herschel Crater stretches roughly 80 miles across. That's huge, considering the moon itself is only about 250 miles wide. The crater takes up nearly a third of Mimas's diameter. The walls of the crater rise about 3 miles high. The central peak inside the crater also towers about 3 miles tall. From a distance, the crater makes Mimas look like a giant eye, or worse, a planet-killing weapon from a movie. The impact that created Herschel Crater nearly tore Mimas apart. Models suggest the moon came within a hair's breadth of being shattered entirely. Just a slightly larger impactor, just slightly more energy, and Mimas would have broken into pieces, probably forming a new ring around Saturn, instead of staying a moon. Some scientists have even traced fracture lines across the far side of Mimas that match perfectly with shockwaves from the Herschel impact. The cracks traveled all the way through the moon and out the other side, leaving scars on the opposite hemisphere. Mimas has another oddity that scientists struggled to explain. Its orbit and rotation pattern is slightly weird. The moon wobbles in a way that suggests its interior may not be uniform. One leading theory is that Mimas hides either an unusually shaped rocky core or a liquid layer beneath its surface, similar to Enceladus, but better hidden. If Mimas does have a subsurface ocean, then it would join the growing list of moons in the outer solar system that secretly contain liquid water. Researchers are still arguing about which interpretation fits the data better. The implications are interesting. Mimas sits closer to Saturn than Enceladus. If it has tidal heating sufficient to keep an ocean liquid, then several other small icy moons across the solar system might be hiding their own seas. The galaxy could be full of these secret worlds, hidden oceans quietly sloshing under frozen crusts, possibly home to chemistries we haven't begun to imagine. For a Saturn-bound crew, Mimas would be both a curiosity and a navigational landmark. Its huge crater would be visible from far away, an easy target to lock onto with telescopes. Its low gravity would make landing technically simple. A spacecraft could touch down on its surface with minimal fuel, almost gliding to a stop. Astronauts could walk around in low-gravity boots, bouncing across an ice landscape, looking up at Saturn filling half the sky. But Mimas isn't the strangest moon in Saturn's collection. Far from it. Out near the edge of the system, an even weirder world orbits. A moon with two faces, one side bright, one side dark. A mystery scientists have debated for centuries and still cannot fully solve. Iapetus is one of the strangest objects in the entire solar system. Not because of what it does, because of what it looks like. The moon is split, almost perfectly, into two completely different halves. One side is bright, almost as white as snow. The other side is dark, almost as black as coal. The contrast is so extreme that early astronomers looking through their telescopes sometimes couldn't see Iapetus at all when its dark side was facing Earth. They thought the moon had disappeared. It hadn't. The dark side was simply too dim to show up against the blackness of space behind it. Iapetus measures about 900 miles across, making it Saturn's third largest moon. The light side has the reflectivity of fresh snow. The dark side reflects only a few % of the light that hits it. The boundary between the two halves is sharp. You don't see a gradient, you see a line, almost like someone painted the moon with a giant brush. For more than 300 years, astronomers debated what could possibly cause such a stark divide. Was the dark material some kind of paint sprayed onto one hemisphere? Was the moon somehow cooked on one side by passing radiation? Did some catastrophic impact strip away the light material on one half and not the other? Cassini finally cracked the mystery partly. The dark material on Iapetus appears to be dust. Specifically, dust drifting in from a distant outer moon called Phoebe, which orbits Saturn in the opposite direction and sheds material into space as it gets pelted by micrometeoroids. That dust slowly spirals inward towards Saturn. When it reaches Iapetus, it hits the leading hemisphere, the side facing forward, as the moon moves in its orbit. The trailing hemisphere stays clean. But that explanation only goes so far. The dark deposit on Iapetus is not just a thin coating. In places it appears to be hundreds of feet thick. The dust falling in from Phoebe wouldn't normally accumulate to that depth. So scientists added a second piece to the puzzle. Once the dust started darkening one hemisphere, that hemisphere absorbed more sunlight. The temperature rose just slightly. Water ice on the dark side started to slowly evaporate over millions of years. The vapor migrated to the cold, bright side and refroze. The result was a feedback loop. The dark side got darker as it lost ice. The bright side got brighter as it gained ice. Over billions of years, the contrast grew into the extreme we see today. That's the current best explanation. It works. It fits the data. But scientists are still uncertain about all the details. Iapetus has other strange features too. A giant equatorial ridge of mountains, stretching almost halfway around the moon, towering up to 13 miles high. The ridge is so unusual that some researchers proposed wild explanations for it, ranging from collapsed orbital rings to ancient tidal bulges left frozen in place. For a Saturn-bound crew, Iapetus would be a strange destination. Bright on one side, dark on the other. Crossing the boundary, astronauts would walk from glittering ice fields into something that looks like a coal mine, with the line between them visible underfoot. The mountains of the equatorial ridge would dominate the horizon, casting long shadows in the dim, distant sunlight. And as you stood there, the cold would creep into everything, because at Saturn's distance, the universe is colder than humans have ever experienced. If you stepped out of your ship near Saturn without a suit, you wouldn't have time to die from suffocation. The cold would freeze you first. Saturn's neighborhood sits at roughly minus 290 degrees Fahrenheit. That's the average temperature of moons like Titan and Enceladus. In some places, it gets even colder. Surface temperatures on certain shadowed regions of Saturn's moons can drop to nearly minus 350 degrees Fahrenheit, approaching the temperature where atoms themselves stop moving. To understand what this means, think about Earth's coldest places. The lowest temperature ever recorded on Earth was at the Vostok Research Station in Antarctica, where thermometers hit roughly minus 129 degrees Fahrenheit. That's cold enough to freeze exposed skin in minutes, to crack metal, to make ordinary materials brittle as glass. Saturn's neighborhood is more than twice as cold, the kind of cold where the metaphors stop working, because nothing on Earth experiences temperatures like this naturally. Materials behave differently when they get this cold. Rubber becomes brittle, plastics shatter, lubricants in machinery freeze solid. Electronic components that work fine at room temperature stop functioning entirely. Cassini's engineers had to design every system on the spacecraft to handle the extreme cold of Saturn's space. Components were tested in cryogenic chambers, frozen and thawed hundreds of times, to make sure they wouldn't crack or seize. For human crews, the cold becomes a constant adversary. Every airlock cycle risks frost damage. Every spacewalk requires suits with built-in heaters drawing massive amounts of power. A failure in a heater system, even for a few minutes, could mean amputation of fingers or toes. A complete suit failure outside the ship would kill an astronaut faster than vacuum or radiation. The body would lose heat so rapidly that even a perfectly insulated suit, if the heater stopped, would offer only minutes of protection. Water ice at Saturn's distance behaves like rock. The ice making up the surface of Titan, Enceladus, and most other Saturn moons is so cold that it has the hardness of granite. Drilling into it would require techniques more like quarrying stone than chipping ice. Heat applied to melt the ice would have to fight not just the temperature, but also the surrounding cold of the air, which would refreeze any meltwater almost instantly. The cold also does something unsettling to human biology. Even with perfect insulation, the body fights constantly to maintain core temperature. Calories burn faster. Blood gets redirected away from extremities to protect organs. Astronauts working in Saturn's environment would need to eat substantially more food just to stay warm. Their resting metabolism would climb. Their sleep would be restless as their bodies struggle against thermal stress, even inside heated quarters. And here's the strange part. Time itself seems to slow down in this kind of cold, not in the physics sense, but in the human sense. People who work in extreme cold often describe a feeling that everything is moving in slow motion. Their reactions slow, their thoughts thicken, their fingers refuse to obey commands fast enough. It's a kind of cognitive frostbite. The brain, getting less blood, starts to throttle back. Mistakes happen. For a crew working on Saturn's moons, every action would carry this hidden weight. The cold isn't just dangerous, it's exhausting. It eats at the edges of every plan. But cold is just one of the strange things deep space does to the human body. There are stranger changes still, things that happen to your blood when gravity disappears for years at a time. In space, your blood gets confused. Here's what happens. Down on Earth, gravity constantly pulls your blood toward your feet. Your circulatory system fights back, pumping the blood upward, keeping it moving. Valves in your veins prevent backflow. Muscles in your legs squeeze on every step, helping push blood back to the heart. The whole system evolved over millions of years to function in the specific gravitational field of our planet. Take away gravity and the whole arrangement breaks down. Blood no longer pools in the legs. Instead, it shifts upward toward the head and chest. Astronauts report puffy faces, congested sinuses, and a constant feeling of having a slight head cold. Within hours of reaching orbit, the body senses too much blood in the upper region. It starts dumping fluid. Astronauts urinate more frequently. Their total blood volume drops sometimes by 20% over the first weeks of a mission. That sounds harmless until you remember what blood does. Less blood means less oxygen delivery, fewer red blood cells, smaller heart muscle as the heart adjusts to its lighter workload. The cardiovascular system essentially powers down to match the lower demand. For a short stay in space, this is fine. The body recovers within weeks after returning to gravity. For a multi-year mission to Saturn, the changes compound. Then there's the strange business of standing up. After a long time in zero gravity, the act of standing in any gravity field, even weak gravity, becomes treacherous. The heart, weakened and undersized, struggles to push blood up to the brain against the pull. Astronauts coming back from long missions often faint when they try to stand. Their blood pressure drops the moment they're upright. Their vision goes dark. They collapse. Now imagine the first humans on Titan. After 4 years of weightless travel, their hearts shrunken and lazy, they descend through the orange atmosphere and step onto the icy surface. Titan's gravity is weak, about 1/7 of Earth's, but it's still gravity. Suddenly, blood that has been floating freely for years has weight again. It rushes downward. The astronauts feel dizzy. Some collapse on their first step. The crew's medical officer, herself struggling with the same problem, has to evaluate everyone before any meaningful work can begin. This is one of the reasons why mission planners obsess over artificial gravity. Spinning sections of a ship can simulate gravity by centrifugal force. Astronauts inside a rotating section feel pushed outward, which feels like weight. Spend enough time in artificial gravity each day, and the body might maintain something close to normal cardiovascular health. But spinning sections add complexity. They require precise engineering. The rotation has to be carefully calibrated, or astronauts get motion sickness. The structures need to be enormous to avoid producing dizzying short radius rotation. Beyond the heart, blood does other strange things in space. The cells themselves seem to age differently. Studies on the International Space Station have found changes in the immune system, in white blood cells, in the way platelets clot. Dormant viruses can wake up. Wounds heal more slowly. Bacterial infections spread differently. The whole closed system that keeps you alive starts behaving in ways that medicine hasn't fully mapped. And while blood gets confused, something else is happening at the same time. Something underneath. Your skeleton itself is dissolving, one tiny piece at a time, faster than your body can rebuild it. A slow erasure that turns the strongest material in your body into something brittle and fragile. Your bones are not as solid as they look. They might feel like stone when you knock on your knee, but inside, bone is alive. It's constantly being torn down and rebuilt by specialized cells. Osteoclasts break old bone material apart. Osteoblasts lay down new bone in its place. The two processes balance each other in a healthy adult. Bones stay strong, dense, and resilient. In space, that balance shatters. Without gravity pressing down on your bones, the body decides it doesn't need them as strong anymore. The osteoblasts slow down. the osteoclasts keep working. The result is a steady drain of calcium and other minerals out of your skeleton. Astronauts on the International Space Station lose roughly 1 to 2% of their bone density per month, especially in weight-bearing bones like the hip, the spine, and the legs. Per month. Stretch that across a multi-year Saturn mission, and the numbers become terrifying. By the time the crew arrived at Saturn, their hips and spines could have lost a third or more of their original bone mass. They would have the skeletons of people in their 80s. Possibly worse, the bones become so brittle that even minor stresses can cause fractures. A hard landing in low gravity, a bump against a metal panel, lifting a piece of equipment the wrong way. Any of these could shatter bone in ways that would never happen back on Earth. The lost calcium has to go somewhere. It enters the bloodstream, where it can build up in unhealthy concentrations. Astronauts on long missions sometimes develop kidney stones from excess calcium in their urine. These stones can be excruciatingly painful and, in the worst cases, can block urinary function entirely. Treating a kidney stone in deep space, without specialist equipment, without backup surgeons, without access to anything but the medical kit on board, would be a nightmare scenario for any mission doctor. The bone loss affects more than just the skeleton. Bones contain marrow, where blood cells are produced. As bone mass declines, marrow function can change. Red and white blood cell production may shift. The immune system, already weakened by other space-related changes, takes another hit. Over enough years, the crew's ability to fight infection, heal wounds, and recover from injury would degrade significantly. Engineers have tried for decades to combat this problem. Exercise helps, but doesn't fully prevent the loss. Astronauts on the International Space Station spend about 2 hours per day on resistance machines, treadmills, and stationary bikes, all designed to load their muscles and bones with as much stress as possible. Even with all that effort, the bones still lose mass. The exercise slows the decline, but cannot stop it. Drugs offer some help. Bisphosphonates, the same medications used to treat osteoporosis on Earth, have been tested in space. They reduce bone loss somewhat, but they come with side effects, and they don't restore lost bone. They merely slow the rate of erosion. The only true solution is artificial gravity. A spinning section of the ship, large enough to create comfortable simulated weight, would let the bones experience the same daily stress they do on Earth. Build it large enough, and the crew could live nearly normal physiological lives during transit. But again, the engineering is daunting. The structures required are enormous, complex, and untested in working form. Even with bones intact and blood circulating, another invisible enemy waits. Not in the body, in the mind. The slow, grinding pressure of being trapped, alone, far from home, for longer than any human ever has been. Imagine waking up every day in a small metal room with the same 4 people, for 4 years, with no escape, with no real news from home, with the knowledge that if anyone snaps, if anyone hurts another crew member, if anyone simply has a mental breakdown, there is no one coming to help. This is the psychological reality of a Saturn mission. And space psychologists, the researchers who study how humans handle extreme isolation, will tell you flatly, they are more worried about the minds of a Saturn crew than they are about any of the engineering challenges. Earth-based analog missions give some hint of what to expect. Researchers have run long-duration simulations where crews of 4 to 6 volunteers live in sealed habitats for months at a time, communicating with the outside world only on simulated delay, doing the kinds of tasks future Saturn crews would do. The results are consistent. After a few months, crew tensions rise. After 6 months, interpersonal conflict becomes a constant low-grade hum. After a year, crews show signs of significant psychological stress, sleep disorders, mood swings, reduced cognitive performance, episodes of depression and anxiety. These are volunteers who know the experiment ends. They know the door will open. They know rescue is in the worst case, a phone call away. Now imagine the same conditions, but the door doesn't open. The phone call would take 3 hours to receive a reply. The duration isn't a year, but 8 years. The psychological pressure builds in ways nobody on Earth has ever fully experienced. Astronauts on the International Space Station who serve 6-month rotations report a strange phenomenon called the third quarter effect. About 3/4 of the way through their mission, when the end is in sight but still distant, they hit a wall. Motivation drops. Irritability spikes. Some astronauts describe feeling almost paralyzed by the weight of the remaining time. A Saturn crew would hit this wall not once but several times. The trip out, the arrival period, the trip back. Each phase would have its own psychological cliffs. Then there is the loneliness specific to deep space. On the International Space Station, astronauts can look out the window and see Earth filling their view. They can see weather patterns, continents. Sometimes, if conditions are right, they can identify their hometowns from orbit. Earth is right there. They are still connected visually to the world they left. Beyond the asteroid belt, that connection disappears. Earth becomes a dot. By Saturn, it's a faint star. Astronauts could go entire weeks without bothering to look for it, because finding it would require effort and binoculars. The psychological impact of this visual disconnection is poorly understood. No human has ever experienced it. Lab studies suggest it could be profound. Some space psychologists worry that crews might develop a kind of detachment from Earth itself, a sense that the home planet has become abstract, theoretical, no longer real in the way it used to be. Other psychological risks include religious or spiritual crises, especially as crew members confront the immensity of space firsthand. The shifting sense of time, the strange dreams astronauts often report, vivid and disturbing, possibly linked to changes in sleep architecture in zero gravity. A few crew members might come back fundamentally changed, quieter, more withdrawn. Some, in the worst case, might not come back at all, in the sense that the people who land on Earth would not be quite the same people who left. And the psychological strain becomes harder still when you add the next pressure, knowing that the universe outside your ship is full of invisible deadly particles you cannot block. There's a class of cosmic ray that haunts mission planners more than any other: galactic cosmic rays. High-energy particles, mostly the cores of heavy atoms, traveling at almost the speed of light. They come from outside our solar system, born in the explosions of distant stars or the violent disks of distant black holes. They scream through space in every direction, all the time, everywhere. The problem with these particles is they can punch through almost anything humans can build. Standard shielding doesn't stop them. Lead doesn't fully stop them. Aluminum hulls actually make them worse by creating cascades of secondary particles when the cosmic rays hit. The deeper engineers have looked at this problem, the more discouraged they've become. Each individual galactic cosmic ray is bad news for the cells it passes through. Imagine a microscopic bullet fired through your body at near light speed. As it travels, it leaves a track of destruction behind, ionizing atoms, breaking molecular bonds, damaging DNA in the cells along its path. Most of this damage gets repaired by the body's own mechanisms. Some doesn't. The unrepaired damage accumulates, increasing the risk of cancer, cataracts, and other long-term health problems. For astronauts on the International Space Station, who get partial protection from Earth's magnetic field, this exposure is manageable. They receive carefully tracked radiation doses, and NASA limits how many missions any astronaut can fly to keep lifetime exposure below safety thresholds. On a Saturn mission, the math falls apart. The crew would receive roughly hundreds of times more radiation per day than they would on the International Space Station. Even with the best feasible shielding, every crew member would absorb a lifetime's worth of radiation, possibly much more, over the course of the mission. Cancer risk would climb. The actuarial estimates run from worrying to grim. depending on the assumptions you make about shielding effectiveness. But the long-term cancer risk isn't even the scariest part. The truly disturbing finding came from laboratory experiments on animals exposed to similar particles. Mice and rats subjected to galactic cosmic ray equivalents showed changes in their brains. The particles damaged neural pathways. The animals developed cognitive problems, memory issues, anxiety, reduced ability to solve problems. The damage was real, measurable, and in some cases progressive. For a Saturn crew, this raises a horrifying possibility. The astronauts trained for years to handle the mission. They drilled emergency procedures until the responses became automatic. They learned the math, the engineering, the medical procedures. Then slowly the cosmic rays passing through their heads could start to chip away at all of it. By the time they reached Saturn, would they still remember everything they trained for? Would they still be able to think as sharply, react as quickly, make the calls a commander needs to make? Shielding solutions have been proposed, but none are easy. Thick water shielding works, but is enormously heavy. Magnetic shielding, where the ship generates its own protective field, exists in theory, but no working version has flown. Some designs propose creating a hollow water-filled shell around the crew's living quarters. Others suggest using the ship's fuel as a radiation barrier, which works until you start burning it. For now, every Saturn mission plan accepts a degree of radiation damage as unavoidable. The crew would not come home unscathed. They would carry invisible scars in their cells, their brains, their immune systems for the rest of their lives. And the trip itself, with all its dangers, depends on something even more fragile: the food the crew brings with them, packed at launch, with no possibility of resupply for years. A human being needs roughly 2,000 calories per day to function. Multiply that by 4 crew members. Multiply that by 8 years of round-trip travel time. Add a safety margin for delays, emergencies, unexpected extensions. The number that comes out is staggering. A Saturn crew would need to launch with something like 24,000 person days of food, tens of thousands of meals, all of it crammed into the ship from day one. Now consider the constraints. The food has to be lightweight because every pound matters. The food has to last for years without spoiling because there's no refrigeration on the scale needed. The food has to be safe from radiation damage. The food has to provide adequate nutrition across the entire spectrum of human dietary needs: protein, carbohydrates, fats, vitamins, minerals, fiber. And the food has to be palatable. This last requirement sounds soft, but it's actually critical. Astronauts who eat the same boring meals day after day stop eating enough. They lose weight. Their morale crashes. Their immune systems weaken further. NASA discovered decades ago that food variety isn't a luxury on long missions. It's a medical necessity. Current space food technology can stretch some items for years. Freeze-dried meals, properly packaged, can last 5 years or more without significant nutrient loss. Certain canned and pouched items can last even longer, but not everything keeps. Fresh fruits and vegetables, which provide essential vitamins, can't be stored that long in any practical form. Crew members on long missions would have to rely on supplements, fortified foods, and possibly small onboard gardens. Growing food in space has been tested in limited ways. Astronauts on the International Space Station have successfully grown small batches of lettuce, herbs, and a few other crops. The yields are tiny compared to what a crew would actually need to live on. But the technology is improving. A Saturn mission might carry a hydroponic garden capable of producing supplementary fresh greens, perhaps even small amounts of fruit. The garden would also serve psychological purposes, giving crew members something living to tend in a metal environment. Water is a different challenge. A person needs about 3 to 4 pounds of water per day for drinking and hygiene. Multiply across 4 crew and 8 years, and the numbers become impossible to launch in raw form. The solution is recycling. The International Space Station already recycles roughly 90% of its water including from astronauts' sweat, urine, and exhaled humidity. A Saturn mission would need to push that recovery rate close to 98% or higher. Every drop matters. Oxygen is another recycle problem. Humans exhale carbon dioxide and consume oxygen. On a long mission, this requires systems that can pull carbon dioxide out of the air and either store it, release it, or split it back into oxygen. Some designs use plants to help with this, treating the onboard garden as a partial air recycler. Others rely on chemical and electrical processes to separate oxygen from water or carbon dioxide. A single failure in any of these life support systems could doom the crew. A broken water recycler, a failed oxygen generator, a blocked carbon dioxide scrubber. Each of these would create a crisis within hours. With years of travel ahead and no resupply possible, the crew would have to repair the equipment with the tools and spare parts they brought, or die. So the Saturn ship would be, in many ways, a fragile bubble of life floating through an environment that wants to kill it. And the worst part is what comes after, because returning to Earth, with everything that's gone wrong on the way out, is somehow even harder than getting there. For most space missions, the return is the easy part. You launch from Earth, you go somewhere, you come home. Gravity does most of the work on both ends. Earth pulls you back down whether you want it to or not. For Saturn, the math reverses. Getting there is the trip. Coming home is the impossible part. Here's why. When you launch from Earth towards Saturn, you're traveling roughly outward in the solar system. You're climbing up out of our nearest star's gravitational well, but you're also flying along with Earth's motion around that star. You can use clever maneuvers to swing past Venus or Jupiter and pick up speed from their gravity. The trip is long, but the energy requirements are manageable. Coming back, the situation flips. You need to lose speed, drop back down into the inner solar system, and arrive at Earth at exactly the right moment in Earth's orbit. The timing has to be perfect. Earth doesn't wait. The planet keeps orbiting our nearest star at roughly 67,000 miles per hour. If you arrive at Earth's orbit even a week early or a week late, you miss the planet entirely. You'd find yourself in empty space, with Earth millions of miles away. So return trips require precise launch windows. The ship has to leave Saturn at exactly the right moment to intercept Earth, at exactly the right point in its orbit. Miss the window, and you wait. Sometimes for years. The next opportunity might not come for a long stretch of time. Then there's the fuel problem. Returning from Saturn requires nearly as much fuel as getting there in the first place. The ship has to accelerate inward, then decelerate to enter Earth's orbit safely. All of that fuel has to be carried out to Saturn with the original mission, or somehow manufactured on a moon of Saturn before the return trip. Manufacturing fuel in deep space, called in situ resource utilization, exists in concept but has never been done at the scale a Saturn return would require. One promising idea involves Titan's atmosphere. The moon contains huge amounts of methane and other hydrocarbons. In theory, a future mission could land on Titan, refine the methane, combine it with oxygen extracted from Titan's water ice, and produce rocket propellant. The astronauts would refuel the return vehicle on the moon itself before launching back home. This would save enormous amounts of launch mass from Earth. It would also require building a chemical refinery on a frozen alien moon, with all the engineering and logistics that implies. If that doesn't work, the return vehicle would have to be sent ahead, robotically, years before the crew launches. The robot ship would arrive at Saturn, set up shop, and start producing fuel autonomously. Only when sufficient propellant was stockpiled would the crewed mission launch from Earth. This approach is currently being studied for Mars missions and may eventually apply to Saturn as well. But the complexity is immense. The pre-positioned robots would have to work flawlessly for years without human supervision. Even with all of these technical solutions, returning from Saturn means accepting a significant chance of failure. Every system has to hold. Every calculation has to deliver its load on demand. Any breakdown could strand the crew permanently. They would die out there. Their bodies, frozen and preserved in the deep cold of space, might never be retrieved. And the orbital mechanics that allow return also create another problem. A problem so subtle that most people don't think about it until it locks them in. The way the planets move forces certain decisions early, decisions that cannot be undone once made. Space travel doesn't work like driving a car. You don't simply point your ship toward your destination and accelerate. The math is more complicated. The ship and the destination are both moving. Fuel is precious. To save fuel, mission planners use a trick called the gravity assist, or slingshot. Here's how it works. A ship flies close to a large body, like a planet, and uses that planet's gravity to bend its trajectory and pick up speed. The planet doesn't lose noticeable energy from this because it's so massive. The ship, in comparison, gets a major boost, like a slingshot rock being flung outward. Multiple gravity assists can be chained together. A typical mission to Saturn might use a flyby of Venus, then Earth, then Jupiter, gaining speed at each stop before finally reaching its destination. The trick is that gravity assists lock you into a specific trajectory. Once you launch on a particular path, the windows for each gravity assist arrive at fixed times. Miss one, and you might miss the next, and the next. The whole plan unravels. For a Saturn mission, the gravity assist schedule typically depends on Jupiter. The ship leaves Earth, swings by Jupiter, and uses the gas giant's gravity to fling itself outward towards Saturn. Without that Jupiter flyby, the trip takes much longer and uses much more fuel. With it, the trip is faster and cheaper. But the timing has to be exact. Jupiter has to be in the right place when the ship arrives. Saturn has to be in the right place a few years later, when the ship arrives there. Everything has to align. This creates a kind of trap. Once the ship launches and commits to its trajectory, the path is largely set. The crew can't simply decide to turn around and go home. Their orbit is locked into the gravitational geometry of the entire solar system. Changing course requires fuel they don't have. They can adjust their trajectory in small ways, but the broad path is fixed. What this means in practice is that decisions made years before the mission, by mission planners back on Earth, become permanent constraints on the crew. The ship was built for a specific trajectory. The fuel was calculated for that trajectory. The crew's lives depend on the trajectory working as planned. If something goes wrong out there, if a system fails or a crew member becomes ill, the options for response are limited by the orbital mechanics that locked in at launch. There's something psychologically heavy about this. The crew is not free to make choices in the way people on Earth are free. Their movements are dictated by the math of the solar system. Their fates are partially sealed before they even leave the launch pad. They can affect small things, repair minor systems, adjust internal schedules, conduct experiments. But the big picture, when they arrive, how long they stay, when they return, is determined by physics they cannot change. The same orbital mechanics make rescue impossible. If a crew on Saturn called for help, even if Earth instantly launched a rescue mission, that mission would have to wait years for the right launch window, then take years more to arrive. By the time help got there, the crew would have either solved their problem on their own or died. Rescue is theoretical, not practical. So out there in the dark, with their trajectory locked and their options limited, the crew would face every problem alone, every emergency, every failure, every illness. And out of all the things that could go wrong, the worst is the kind of failure that nobody trained for. A spacecraft is essentially a small ecosystem held together by engineering. Air to breathe, water to drink, power to run everything, heat regulation, pressure containment, communications, navigation. All of these systems have to work continuously for the entire duration of the mission. A single critical failure can end everything. Mission planners build in redundancy wherever possible. Critical systems have backups. Backups often have backups. The International Space Station, the most complex inhabited spacecraft ever built, has multiple redundant systems for every life-critical function. If one oxygen generator fails, another takes over. If one carbon dioxide scrubber fails, another kicks in. The whole machine is built to keep working through individual breakdowns. A Saturn mission would push redundancy to extremes. Triple or quadruple redundancy on every life support system. Spare parts for every component that might fail. Tools to manufacture replacement parts when stocked spares run out. Even with all of this, the laws of probability suggest that failures will happen. Over 8 years of operation, in a high-radiation environment, with no possibility of outside help, some systems will break in ways the crew didn't predict. The most dangerous failures are the ones that take down multiple systems at once. A power failure could cripple life support, communications, and navigation simultaneously. A pressure breach could vent the atmosphere, freeze the water, and kill the crew before they reach their suits. A computer crash could cascade through every automated system on the ship, leaving the crew flying blind. History gives us examples of close calls. Apollo 13, the famous near disaster, was triggered by a single failed oxygen tank. The explosion crippled the spacecraft, forcing the crew to rely on their lunar lander as a lifeboat for the trip home. The crew survived because Earth was close enough for ingenious mission control to talk them through every step. They returned, alive, though battered. On a Saturn mission, an Apollo 13-style emergency would not have the same outcome. Even with the best mission control on Earth, communications take more than an hour each way. By the time the crew explained their problem, an hour and a half would have passed. By the time Earth responded with solutions, another hour and a half would have passed. 3 hours, minimum, between problem and possible solution. In an oxygen emergency, the crew might not have 3 hours to wait, so Saturn crews would have to be largely self-sufficient in emergencies. They would need to diagnose their own problems, design their own fixes, and implement them with the materials at hand. They would need to be engineers, doctors, chemists, electricians, and surgeons all at once. They would need to handle the kind of unprecedented situations that would terrify a full ground team back home, alone, in seconds. Training for this kind of resilience is hard. You can't really simulate the experience of being on your own with no backup. Earth-based training inevitably involves trainers and support staff and known answers. The real thing, when it happens, would be different. The crew would face situations no one had anticipated, with consequences they could not predict. A single broken pump, a single cracked seal, a single failed circuit board. Out there, any of these could be the start of a chain reaction that ends with the crew dead and the ship drifting silently through the dark. A tomb that will eventually fall toward our nearest star or be flung out of the solar system entirely. And the dangers don't end with the ship's internal systems. The space the ship is flying through has its own quiet hazards. Particles too small to notice that gradually eat the ship from the outside, one tiny impact at a time. Space looks empty. From a distance, it seems like a perfect vacuum. Nothing there, nothing to worry about. But the truth is different. Interplanetary space is full of dust. Tiny grains, some smaller than a grain of sand, drift through the solar system in countless billions. Most of them are debris from comets and asteroids, broken off over millions of years. They orbit our nearest star like a thin, invisible mist, almost everywhere, all the time. For a spacecraft moving at tens of thousands of miles per hour, even tiny dust grains carry serious energy. A grain weighing less than a milligram, hitting at orbital speeds, can produce a small crater on the surface of a spaceship's hull. Over years of travel, these impacts add up. The hull gradually pits, then erodes, then thins. Mission engineers have studied this damage on returned spacecraft. The forward-facing surfaces are usually peppered with hundreds or thousands of tiny craters. Most are too small to see without magnification, but they accumulate. On a Saturn mission, with 8 or more years of total travel time, the dust damage would be far worse than on shorter missions. The cruise ship would arrive at Saturn pitted, eroded, possibly weakened in critical areas. Some of the damage might be repairable in flight. Other damage would have to be accepted as part of the cost of the journey. Worse than the steady drizzle of small dust is the occasional larger impact. Bigger grains the size of a peppercorn or so can punch through outer hull layers and damage internal systems. A direct hit on a fuel line, a power cable, or a pressure vessel could be catastrophic. The chance of any single impact being lethal is small. The cumulative chance over years of travel is much higher. Spacecraft are designed with debris shielding to handle these impacts. The most common design is called a Whipple shield, named after the astronomer who proposed it. A Whipple shield has 2 layers, an outer thin layer and an inner thicker layer, separated by a gap. When a high-speed particle hits the outer layer, it vaporizes or disintegrates into a spray. The spray, less concentrated, hits the inner layer and is absorbed without penetrating. Whipple shields have protected the International Space Station from countless impacts over its years in orbit. For Saturn, Whipple shields would be more elaborate, with multiple layers and reinforced sections around critical systems. Even so, the shielding cannot be perfect. Some impacts will always get through. The crew would have to live with the knowledge that, statistically, at least a few significant hits would occur over the course of their journey. There's another danger from cosmic dust. As the ship moves through the dust field, friction with individual particles slowly accumulates static electric charge on the hull. Without proper grounding and electrical management, this charge can build up to dangerous levels and discharge unexpectedly, frying electronics or shocking crew members. Engineers have to design careful grounding systems and monitor electrical buildup constantly. Saturn's neighborhood adds another twist. The planet's rings are made of countless ice and rock particles, but the rings also shed material into the surrounding space. Tiny fragments drift outward from the rings, forming a more concentrated dust environment near the planet than in deep space elsewhere. Any mission flying close to Saturn would experience higher impact rates in the planet's immediate vicinity. And what waits at the bottom of all that gas, beneath all those crushing layers, may be the strangest substance humans have ever theorized, a material that behaves like a metal, but isn't really a metal, a material we can barely make on Earth. Deep inside Saturn, beneath thousands of miles of compressed gas, sits a substance that may be the strangest material in the entire solar system, metallic hydrogen. To understand what this means, consider that hydrogen is normally the lightest, gentlest element, a gas, the kind of stuff that fills birthday balloons. Up at the top of Saturn's atmosphere, hydrogen behaves normally, drifting around as a gas. But the deeper you go, the more pressure builds. Eventually, that pressure becomes so extreme that hydrogen atoms can't behave like a gas anymore. They can't even behave like a metal. Here's what happens. Under enough pressure, hydrogen atoms get squeezed so close together that their electrons stop being attached to individual atoms. Instead, the electrons flow freely through the whole substance, just as electrons flow through copper wire. This shared sea of electrons is the defining feature of metals. It's what makes metals conduct electricity, reflect light, and behave the way metals behave. So compressed hydrogen becomes, in effect, a strange and exotic metal. This metallic hydrogen layer in Saturn is enormous. It probably starts roughly halfway down toward the planet's core and continues for tens of thousands of miles. The total amount of metallic hydrogen inside Saturn vastly exceeds the entire mass of Earth. It's like having an Earth-sized ocean of liquid metal sitting at the center of a gas giant, a material so extreme that, on our own planet, we can only create tiny amounts of it for fractions of a second in specialized laboratory experiments. The metallic hydrogen layer is responsible for several of Saturn's strange properties. It generates the planet's enormous magnetic field, the same field that creates the deadly radiation belts and dangerous magnetosphere. The currents flowing through metallic hydrogen behave like a giant natural dynamo, churning out magnetism on a planetary scale. The metallic hydrogen layer also contributes to Saturn's internal heat. As the planet slowly settles and adjusts over billions of years, energy gets released from this layer, warming the interior and driving the convection that produces Saturn's wind belts and storm systems. The planet glows with infrared radiation, giving off more heat than it receives from our nearest star. For human exploration, the metallic hydrogen interior of Saturn is unreachable. It exists at depths and pressures no probe could ever survive. Even thinking about studying it directly requires speculative future technology, like submersibles that could function under pressures millions of times higher than at the bottom of Earth's deepest ocean. Such technology is so far beyond current engineering that it's barely science fiction. It's more like a distant hope. What we can study is the surface of the metallic hydrogen layer indirectly. The magnetic field tells us about its electrical properties. Gravity measurements made by spacecraft like Cassini can detect the layer's thickness and density. By analyzing how the planet's mass is distributed, scientists can deduce the rough shape and behavior of the interior. The implications stretch beyond Saturn. Jupiter, the larger gas giant, almost certainly has an even bigger metallic hydrogen layer. Extrasolar gas giants discovered around distant stars may also have similar interiors. Metallic hydrogen, this exotic and almost impossible substance, may be one of the most common materials in the entire universe. We just can't get to any of it. But the deepest mysteries of Saturn aren't all hidden inside the planet. Some are right there on the surface, in plain view, daring anyone to explain them, like the strange hexagonal storm at the North Pole, the one that breaks every reasonable model. Coming back to that hexagon at Saturn's North Pole, because it deserves another look, the more scientists study it, the stranger it gets. The standard explanation, that the hexagon is a stable wave pattern in the atmosphere caused by certain combinations of wind speeds and rotation, works as a theory. It even matches some laboratory experiments where researchers spun tanks of fluid and produced polygonal shapes. But the Saturn hexagon has features that don't quite fit the simple wave model. The hexagon doesn't drift. Most large weather features on planets shift over time, blown around by other systems. Saturn's hexagon stays locked in place year after year. Some scientists have estimated it's been there for at least decades, possibly much longer. Voyager spacecraft saw it in the 1980s. Cassini saw it more clearly in the early 2000s. It's still there now. The hexagon also has unusual depth. It's not just a pattern at the cloud tops. Radar and infrared measurements suggest the geometric shape extends hundreds of miles down into the atmosphere. A standing wave pattern that goes that deep is unusual. Most surface-level patterns on planets are just that, surface level. The Saturn hexagon penetrates far into the planet's depths. The hexagon's color also changes over time. When Cassini first photographed it in detail, the interior of the hexagon was bluish. Years later, as Saturn moved through its long seasonal cycle, the color shifted to golden. The change appears tied to seasonal sunlight patterns at the pole. As the angle of sunlight changes, the chemistry of the upper atmosphere shifts, producing different hazes and changing the apparent color. The hexagon itself, the geometric pattern, stays stable while the colors inside it transform. Inside the hexagon, at the center, a powerful storm rotates. Sometimes called the polar vortex, this storm is itself enormous, with an eye over 1,000 miles across, and winds that scream around its center at hundreds of miles per hour. The storm sits inside the hexagon, contained by it like a hurricane locked inside a geometric cage. The corners of the hexagon are particularly strange. Sharp angles in fluid flow are rare. Most fluids, given enough time, smooth out their sharp features. Saturn's hexagon maintains corners that are crisp and well-defined, with measurable angles close to the geometric ideal of 120 degrees. Some researchers have wondered, whether the corners are the result of unusual wave interactions where multiple wave systems intersect in precise patterns. The hexagon also features bright spots and storm cells inside its boundaries. Lightning has been detected within the structure. Smaller storm systems form and dissipate inside the hexagonal walls, never quite escaping past them. For a Saturn mission, the hexagon would be a centerpiece of observation. It's the kind of feature that, once seen up close, would justify years of analysis on its own. Crews could conduct detailed atmospheric studies, mapping wind speeds, temperatures, and chemical compositions throughout the structure. The data they gathered could transform our understanding of planetary atmospheres in general. If we understand why Saturn produces a stable hexagon, we might better understand the behavior of other gas giants, including extrasolar planets. Yet the hexagon also serves as a quiet reminder of how much we still don't know. The largest, most studied gas giant, within easy reach of our probes, still hides mysteries we can't fully explain. The closer we look, the more questions appear. And Saturn itself spins so rapidly that its day is one of the shortest of any planet. The whole giant world rotates faster than you'd expect. Saturn spins fast, faster than seems reasonable for something so big. The planet completes a full rotation in roughly 10.5 hours. That's it. A Saturn day is shorter than half an Earth day. Despite Saturn being roughly 9 times wider than Earth, the giant planet whirls around its axis in less than half the time our planet takes. This rapid rotation is why Saturn isn't perfectly round. The planet is visibly squashed, flattened at the poles, and bulging at the equator. The bulge is significant. Saturn's equatorial diameter is about 10% larger than its polar diameter. Looking at the planet, you can see the oblate shape with the naked eye through a good telescope. It's not a sphere. It's a flattened, disc-like ball, distorted by its own spin. The fast rotation drives many of Saturn's weather features. The strong wind belts that circle the planet are partly caused by the rapid spin shearing the atmosphere into bands. The huge equatorial winds, blowing at close to 1,000 miles per hour, get their energy from the rotational forces driving the entire planet. Determining Saturn's exact rotation rate proved surprisingly difficult. Unlike rocky planets with solid surfaces, gas giants don't have fixed features you can track easily. The clouds move at different speeds depending on latitude and depth. Different parts of the atmosphere rotate at slightly different rates. Scientists had to use the planet's magnetic field to measure the true rotation of the deep interior, and even then, the answer kept getting refined. For a long time, mission scientists thought Saturn rotated at one specific rate based on radio emissions from its magnetic field. Then Cassini measured the same emissions and got a different answer. The difference was small but real. Saturn's magnetic field seems to wobble slightly, possibly due to interactions between different layers inside the planet. The interior rotation rate may differ slightly from the surface, or from the magnetic field's apparent rotation. The whole picture is more complicated than scientists initially expected. The fast spin has consequences for any future mission. Spacecraft orbiting Saturn have to deal with rapidly changing perspectives as the planet whirls below them. Surface features, if you can call cloud patterns surface features, race past underneath. Photography requires careful exposure timing. Observations of specific weather systems become brief snapshots rather than long studies. The rotation also affects the rings. Saturn's rings rotate around the planet at speeds tied to their distance from the center. Inner rings move faster than outer rings, following the same rules that govern any orbital motion. Because Saturn itself rotates so quickly, the planet's gravitational and magnetic effects on the rings are complex and dynamic. The rings are constantly being shaped by Saturn's spin, by passing moons, and by their own internal physics. For a human crew, Saturn's short day would create an unusual rhythm. Watching the planet from orbit, you would see weather features racing by faster than on any other planet you could ever realistically visit. Storms appear, swirl, and vanish in cycles of just a few hours. The hexagon at the North Pole would complete its rotation in less than half an Earth day. The auroras at the poles would shift and shimmer at speeds tied to the planet's magnetic field, themselves spinning with the same rapid rhythm. The fast spin also means that the planet's seasonal changes, while they happen slowly over Saturn's 29-year orbit, are punctuated by a relentless daily cycle: sunrise, sunset, sunrise, sunset, every 10.5 hours, forever. And in the end, after all the dangers, all the marvels, all the discoveries, the most terrible truth about Saturn might be the one nobody wants to say out loud: the reason no human will ever come back. So here it is, the truth at the bottom of everything. After all the rocket equations, all the radiation belts, all the bone loss and psychological strain, all the diamond rain and metallic hydrogen and hexagonal storms, the deepest reason the first human to reach Saturn would never see Earth again comes down to something simpler than any of these obstacles. We don't have the technology to bring them back. Not now, not soon, possibly not ever in any human lifetime currently being lived. Going to Saturn is a one-way problem with current engineering. Every plan that gets the crew there with reasonable timelines and reasonable budgets either skips the return trip entirely or relies on technologies that don't yet exist. The serious mission designs assume one of three things: either fuel manufacturing on Titan or another moon using local resources with all the complexity that implies, or pre-positioned return vehicles sent years in advance, waiting in orbit for the crew to arrive, or nuclear propulsion of a kind that has been studied for decades but never actually flown with humans aboard. None of these are simple. None of these are close. Each represents a major step beyond what humanity has demonstrated. We can land robots on Mars. We can put telescopes in deep space. We can keep small crews alive on the International Space Station for years at a time. Putting humans on Saturn and bringing them back is several orders of magnitude harder than anything we've actually done. So the first human to reach Saturn, in any realistic scenario, would be making a decision very different from the decisions astronauts make today. Apollo astronauts knew they were coming home. Shuttle astronauts knew they were coming home. International Space Station crews know they're coming home. The first Saturn crew, even if everything works perfectly, would face a journey from which return is not guaranteed and might not be possible at all. Some space advocates argue that we should send people anyway, that the science would be worth it, that the discoveries about Saturn's atmosphere, its moons, its hidden oceans, its strange physics would be worth a few human lives. Others argue that such a mission would be morally indefensible, a waste of brave volunteers, when robotic missions could accomplish nearly the same scientific goals at a fraction of the cost and zero risk to human life. The debate continues, mostly quietly, in the meeting rooms of space agencies and the journals of astrobiology researchers. The technology slowly improves. Each year, propulsion concepts get a little more efficient. Radiation shielding gets a little better understood. None of the individual advances are dramatic. The progress is incremental. But here's the cliffhanger that haunts the dreamers. If humanity ever does send a crew to Saturn, that crew will witness things no human has ever seen. They will float in orbit above the hexagonal storm. They will look at the rings from above, watching the ice catch starlight. They will walk on Titan's beach made of frozen hydrocarbons. They will fly through Enceladus's plumes, sampling the water from a hidden ocean. They will see Saturn fill the sky in ways pictures cannot show. And they will look back, once, toward the inner solar system, and find a tiny blue dot, dimmer than the surrounding stars, and they will think about everyone they ever loved, all packed inside that single point of light. And they will know that they will never touch that world again. The first human to reach Saturn would not come home. They would leave the dot behind. They would become something new. A creature of the outer dark, a witness to wonders, but no longer a child of Earth. The choice, when it comes, will not be easy, but someday, someone will make it.